In the final months of 2025, something begins to unfold in the skies that defies every statistical model astronomers thought they understood. Between September and December, no fewer than 7 major comets will thread their way through the inner solar system. Not over years, not scattered across decades, but all within a compressed 6-month window. It is a traffic jam of cosmic proportions, and it has no modern precedent. Most years are quiet. Maybe one bright comet appears, maybe 2 if observers are lucky. Entire calendar years can slip by without a single object visible to the naked eye. That silence makes the sudden surge even more surreal. To have 7 inbound at once, each bright enough or close enough to command professional attention, is not just unusual. It is vanishingly rare, the kind of outlier that makes statisticians double-check their math. When the Minor Planet Center circulated the orbital updates, even veteran comet hunters admitted they had never seen anything like it. For the first time in decades, professional astronomers reached for a term they almost never use. They called it a swarm event. The phrase alone carries weight. A swarm is not random. A swarm suggests pattern, convergence, choreography. Whether the alignment is truly orchestrated by dynamics we do not yet understand, or whether it is an extraordinary coincidence in a chaotic system, the effect is the same. Earth is about to witness a season unlike any in living memory, a season when the sky itself seems crowded. The first alarms came not from human eyes, but from machines. Automated survey networks, Pan-STARRS in Hawaii, Atlas in Chile, Catalina in Arizona, and the brand new Rubin Observatory in the Atacama Desert, lit up with detections in rapid succession. The cadence of alerts was relentless. Each night brought fresh designations: C/2022N2, C/2025R2, C/2025. K1, one after another, flagged by software tuned to catch the faintest, fastest-moving specks of light against the stars. At first, some believed it was simply a fluke of improved coverage. Rubin, with its sweeping 8.4-meter mirror and panoramic digital camera, can now scan the sky to depths older surveys could never reach. Of course, the numbers would climb, but the logbooks told a different story. Even after correcting for survey bias, the record stood. In the entire digital era, no season had ever recorded more than 4 major comets with perihelion inside 2 astronomical units. This year had nearly doubled it, and the geometry added another layer of unease. The orbits were not scattered randomly across the celestial sphere. Instead, they clustered near the ecliptic plane, the flat highway along which planets orbit the Sun. It meant the comets were not just curiosities for telescopes. They were cutting directly across the corridors where Earth, Mars, and the other inner planets make their circuits. What looked like coincidence on paper began to feel like convergence in reality. As plots of the trajectories circulated online, social media lit up. Graphs showing a spike in detections, 7 times the baseline in less than half a year, spread rapidly, annotated with theories ranging from hidden asteroid breakups to orchestrated warnings. Some called it a statistical hiccup. Others whispered about alignments and patterns humanity was not meant to ignore. Inside professional circles, the tone was more cautious, but no less intense. The phrase repeated itself across forums, seminars, and emergency observing proposals. This should not be happening. One by one, the players in the swarm came into focus. C/2022N2 Pan-STARRS marked the faint outer boundary. Its perihelion lies beyond Mars, its light so dim that only sensitive instruments can track it. For backyard observers, it will be little more than a footnote. But for astronomers, it sets the stage. Pan-STARRS is the opening bracket of the swarm, the quiet first arrival that hints at the drama still to come. Then came the comet that captured headlines, C/2025R2 Swan. Discovered on September 11th, it wasted no time, racing to perihelion the very next day at just half an astronomical unit from the Sun. The real spectacle comes October 21st, when Swan sweeps past Earth at a distance of only 37 million kilometers, a mere quarter of the gap between our planet and the Sun. That geometry is perfect for pre-dawn observers in the Northern Hemisphere. Forecasts predict a tail stretching 2.5 degrees across the sky, 5 times the apparent width of the full moon. For millions of people, Swan will not be a line of data in an observatory log. It will be a glowing apparition, a rare naked-eye visitor visible without a telescope. Hot on its heels comes C/2025 K1 Atlas. Its trajectory will carry it closer to the Sun than Mercury itself, a perilous dive to just 0.33 AU. The intensity of that pass means volatility. Astronomers expect violent outbursts as buried ices rupture under solar heat, ejecting gas and dust in unpredictable jets. It could flare dramatically, or it could fragment outright, disintegrating under stresses too great to survive. Atlas is the wild card, the unstable performer of the group, and telescopes worldwide will be watching for sudden changes in brightness that could signal an explosion of activity. The next act is C/2025 A6 Lemon, and for the general public, it may be the most spectacular of all. Predicted to reach magnitude 3.5 to 4 in early November, Lemon will be visible to the naked eye after sunset in the northern hemisphere. Its evening placement makes it accessible to casual observers, the kind of comet that dominates news headlines and draws people outside to point at the sky. For many, Lemon will be the comet of a lifetime, its luminous tail hanging in twilight skies as autumn deepens. But the list does not end there. 414p/stereo, a faint periodic comet with a perihelion of 0.52 astronomical units, will slip through near the sun's glare, more suited to spacecraft imaging than ground-based telescopes. And 240p/NEAT, though small and distant, will round out the sequence, its presence another reminder of how crowded the inner system has become by year's end. Individually, these objects would have been noteworthy. Together, they are something else, a sequence so tight, so unlikely, that even the most conservative researchers are struggling to explain it. Was this simply the lottery of orbital mechanics, a fluke of long-period comets returning together after eons in the dark? Or was there something hidden in the statistics, a resonance, a trigger, an underlying rhythm in the solar system that humanity had never seen until now? When a comet nears the sun, it changes in ways that no other body in the solar system does. From a distance, it is just a lump of frozen rock and ice, a relic of formation. But as sunlight reaches it, the surface begins to boil. Gas and dust erupt into space, and within days, the object sprouts not one, but two distinct tails. And if you're fascinated by these rare cosmic transformations, don't forget to hit that like button and subscribe. It helps us keep bringing you these deep dives into the mysteries above. The first is the dust streamer, pale, broad, and sculpted by sunlight itself. It arcs away from the comet's path, curving gently, pushed by radiation pressure and gravity. This is the tail most people picture, the wide brushstroke that makes comets visible across the night sky. The second tail is stranger, a narrow electric blue filament. It is made of charged particles, ripped from the nucleus and carried away by the solar wind. This ion tail is not passive. It is a living tether, locked to the magnetic field lines streaming outward from the sun. But that tether can snap. In the chaotic environment of solar maximum, magnetic reconnection events are common. A coronal mass ejection, 1 billion tons of plasma thrown into space, can shift the interplanetary magnetic field in minutes. When a comet is caught in that storm, its ion tail cannot keep up. The old filament tears loose, drifting into the void, while a new one forms instantly, aligned to the new magnetic geometry. To the human eye, it looks like a comet shedding its own spine. Astronomers call it a tail disconnection event. The most famous example came in April 2007, when NASA's STEREO spacecraft recorded a CME slamming into Comet Encke. The footage showed the tail ripping away cleanly, leaving a gap near the nucleus, then floating off like a ghost while the comet immediately regrew a fresh tail in the CME's wake. It was a textbook demonstration of a process once confined to equations and lab plasma simulations. For the first time, the solar wind's hidden violence was written across the sky in real time. Now, the stakes are even higher. In late 2025, the sun is approaching its maximum, firing off between 2 and 5 CMEs per week. 7 comets are inbound, several of them cutting across the ecliptic plane where solar storms are most intense. The odds of catching multiple disconnection events in the same season are no longer slim, they are almost guaranteed. Spacecraft like SOHO, Parker Solar Probe, and Solar Orbiter are already on alert, ready to record every flare, every severed filament. Citizen scientists, too, will be watching with binoculars and backyard telescopes, waiting for the moment a glowing tail suddenly fractures, proof of magnetic reconnection happening millions of kilometers away. But as the anticipation builds, so does the argument. Behind the closed doors of scientific conferences, a fierce debate is playing out. NASA's CCMC modeling teams believe the comets are not just observers, but participants. Their plasma halos and streaming dust interact with the solar wind, and under unstable conditions, they might amplify existing instabilities. In simulations, a dense cometary coma crossing a current sheet can bend the magnetic geometry, increasing the chance of a CME erupting. In this view, the comets are tiny triggers, catalysts that nudge an already volatile star into throwing off more storms. But not everyone accepts that. Teams analyzing data from Parker and Solar Orbiter push back hard. To them, comets are passive tracers, useful markers, but not agents. They point to countless examples where comets pass through active regions without sparking anything unusual. In their data, turbulence, small-scale reconnection, and background variability are more important than the presence of any comet. They warn against overhyping the risk, reminding that even dramatic tail disconnections rarely translate into operational impacts for satellites or power grids. The standoff reveals the deeper truth. Humanity still struggles to predict space weather with confidence. Every satellite, every GPS network, every power line on Earth depends on models that may be incomplete. And here, in late 2025, nature has set up a rare natural experiment. 7 comets, peak solar activity, multiple spacecraft watching. Both sides know that whatever happens, the data will be invaluable, either proving that comets can nudge the sun or confirming that they are just markers swept along by larger forces. Yet even as this scientific duel unfolds, one object in the swarm overshadows all the rest. 3I/ATLAS. From the moment its orbit was plotted, astronomers knew it was different. Unlike its companions, its trajectory is hyperbolic, meaning it is not bound to the sun. It is not returning. It is merely passing through. In all of recorded history, only 2 other confirmed interstellar objects have ever been detected. Oumuamua in 2017, a tumbling cigar-shaped rock that vanished before telescopes could pin down its origin, and Borisov in 2019, a comet-like body with a faint tail. Now Atlas becomes the third, and by far the most spectacular. Already its coma has expanded to more than 700,000 kilometers across, nearly the size of Jupiter, and it grows larger with every week. Through the eyepiece of Hubble and the James Webb Space Telescope, its spectrum defies the norms of local comets. Instead of water vapor dominating, its gas is rich in carbon dioxide and exotic volatiles, with water trailing far behind. Cyanide appears only faintly, and the balance of chemicals suggests a birthplace far from our own sun. This is chemistry forged in a different stellar nursery, a fingerprint from another system entirely. The physics is just as startling. The velocity, the steep angle, the hyperbolic eccentricity all confirm its alien origin. Atlas does not belong here, and once it swings past the sun, it will never return. Yet by chance, or fate, it has arrived in the exact same season as 6 other comets, all crowding the inner solar system together. The coincidence is so unlikely that even cautious astronomers admit the timing is eerie. As 3I/ATLAS rounds the sun, it leaves behind a dust trail Earth may cross in 2026, a chance to sample interstellar grains older than our planet. For planetary defense, it's science fiction made real. Yet Atlas is more than chemistry. It's a messenger, proof our solar system is open to visitors from beyond. By perihelion on October 29th, its vast coma and alien gases may already have rewritten textbooks. With 7 comets inbound and the sun at peak volatility, this rare swarm marks both a scientific experiment and a reminder that humanity is not alone in the dark.